Okay, so we're going to start with filtration here and the red and how that works and the pressures associated with that. So basically here's a nephron of the kidney, and a nephron, it all starts here in this thing called the renal corpuscle. Basically what we have is a glomerulus, which is the capillary that leads into this area, and then the part, I'll zoom in. So this part, so this is the glomerulus in red, and then in green is the tubule that goes down and connects to the collecting duct, which ends up going to the ureter and down to our bladder. So in here, we filter things out from the blood, from the plasma, across this little space and into this tubule, and it travels down. As it travels down, it can get reabsorbed into the blood, and then it gets secreted back into the blood. It gets more and more specified as we go down. So basically what happens here is that we have, right here. So we have different things between the tubule and the blood to filter things out. And so they filter by size and charge. But in general, honestly, it's not too specific. It filters out a lot of things, but there's still tons and tons of things that come in here, like a bunch of ions, glucose, amino acids, lactate, tons of different stuff. So, and we'll get to reabsorption later when it gets more specific. But for filtration, how that works, so in order to get things filtered, we need a pressure in the glomerulus that is higher than the capsule pressure. Or so there's this, we learned about BCOP in the last unit. So BCOP works together with this capsule pressure in the tubule, and they are working to get things into the blood. However, this pressure is working to get things out of the blood. So as long as this pressure is higher than these two pressures combined, then we will have filtration. Now, this can be regulated because the blood pressure in the body is always changing, but we need this to stay constant. So what we do, we have a few different ways to do that. We have a couple of different ways called the myogenic response, tubuloglomerular feedback. So basically what happens in the myogenic response, if there's an increase in blood pressure in the body, then we have these stretched calcium channels on the blood near the arterioles. And basically what happens is that if we sense an increase, then without using the nervous system, it just uses these calcium channels, we are able to vasoconstrict the afferent. So this is the afferent arteriole. We're able to constrict that. And so even if this gets bigger and it's more pressurized, we will constrict this and keep what's in here steady and constant. With tubuloglomerular feedback, we can do two things. We can sense a low blood pressure. So if this is skinnier, not as much, kind of weak, low blood pressure, then what happens is that we have these cells, specialized cells called macula densa, that are part of the juxtaglomerular apparatus that sense sodium chloride levels in our blood and how much that's getting filtered. So if it senses a decrease in filtration of sodium chloride, then it'll release nitric oxide, which will vasodilate this afferent. So it'll make this bigger, allowing more blood in, which will keep this pressure steady. It can also sense an increase in blood pressure, and it can release adenosine, which acts as a so it's basically kind of the same thing as the myogenic response a little bit. So it kind of does the same thing, but there's another way to regulate blood pressure through the tubuloglomerular feedback. In extreme low cases, like if you got really, really, really low blood pressure, then we can recruit the nervous system and norepinephrine and angiotensin 2 can be recruited, which will both vasoconstrict the efferent arterioles. So this is the only case we are going to constrict this. So if it's really low, then we'll constrict this, which will kind of back up blood in here, which will increase the pressure, maintaining this constant. Okay. Let me make sure I got all that before I move on. I got tubular glomerular feedback, process of filtration membrane. Okay. Well, I guess there's a couple other things I'll hit on that section real quick. So yeah, I guess being more specific about these layers, we have fenestrate, which is like the first layer. That touches the blood, and that'll filter by size, and all these filter by size and charge basically. Some filter a little more by size, some a little more by charge. The next step, you have the basement membrane, which kind of looks like just a bunch of holes and lets things through. Filters by size and just a little bit by charge. You got these podocytes, which also are just kind of holes in this little membrane thing to let let things in by size and charge. These are both negatively charged. They're going to repel a lot of negatively charged things, like big proteins, for example. It has a certain diameter that they can let things through. It's like 5 to 7 or something like that. I don't think it's 2. No, I take that back. Certain things that go through have a size like 5 to 7. I don't know the exact width of what it can let through, but red blood cells, for example, are like a few thousand, nanometers or whatever. Anyway, much bigger than what these can let through. So they're very specific to size and they're negatively charged, so they repel a lot of negatively charged things. Some of the things we're going to filter in this, sorry, I'm scrolling all over the place, but some of the things we're going to filter include glucose, sodium, water, amino acids, lactate, chloride, calcium, potassium, and bicarbonate. And some things we're also going to filter are metabolites and urea. But these things will end up getting reabsorbed, which we'll talk about later, because those are good things that we need to keep in our body. Okay, I think that's about it. So now I'm going to explain reabsorption. Okay, so going through all these different places. So in the nephron, that looks like this, we have all these different sections. So we have like the proximal convoluted tubule, descending tubule, loop of Henle, ascending tubule, distal convoluted tubule, and then goes into the collecting duct. So at all of those different places, all those different separations, we have different things that get reabsorbed. So again, when we filter things out, it's pretty specific, but not that specific. And so it's just going to let a bunch of these things through. But we don't want all those things into the urine, and so we need to reabsorb some of those things. So basically it goes filtration, reabsorption, and then things get secreted back into the tubule. So what's it? Filtration, reabsorption into the blood, then secretion, and then excretion. So just more as you go down, this gets more and more specific. So in the proximal convoluted tubule, that's where we have most of the stuff that gets reabsorbed. So sodium is a big player in all of these different parts. So what happens is that we have these channels along. So this is the tubule. This is the lumen, or the cells that are in between the tubule and the blood, and this is the blood. So on this side, we have sodium that drives a lot of these things in, like amino acids, glucose, and lactate. So they drive in, and we have specialized channels going into the blood that allow all these things through. And these things we filter soon and quickly, and we filter all of it. Because we don't, for example, with glucose, we don't want any of that in the urine because that means we have diabetes. The reason sodium can be such a big player is because of the gradient established by the sodium-potassium pump. That sodium-potassium pump comes in a lot of different places and helps maintain the resting membrane potential and helps just create gradients, because a lot of these things are driven by gradients, like lactate, glucose, and amino acids. Those are driven by the sodium gradients to let things in by secondary active transport or it's just like the driver and passenger method of indirectly uses ATP. So this is using ATP to get it out, and this is just using gradients to get it back in. Anyway, so those are filtered there or reabsorbed. Another thing reabsorbed, very important, is bicarbonate, because we need that to buffer things when we get acidic or whatnot. How that happens, if you have CO2 in the blood from breathing, comes in, joins with water, makes carbonic acid, which splits into bicarbonate and protons. Bicarbonate goes this way, protons go this way, and that is also secondary passive or secondary active transport, because sodium is pumped in by the gradient, and this is an antiport, which allows protons out. That then combines with bicarbonate here, make carbonic acid, which splits into water and CO2. As all these things are coming through, we get this thing called solvent drag, which is basically just these two ions, calcium and potassium. They follow everything else that's going through. And so those things are reabsorbed. So we got these three things, bicarbonate, calcium, and potassium reabsorbed. We also have water. Water follows salt, and so anytime sodium is going to go this way, which is because in this case in a lot of cases we have sodium coming into the cell here again, and we can have a sodium-potassium pump pumping sodium into the blood, and that's going to follow water. So water is another big thing that is put in the blood there. In the proximal straight tubule, one of the big things filtered is chloride. What happens is protons with that same pump that we described above, it'll combine with an anion outside. When it combines, it can easily flow through the membrane into this lumen, and then it immediately splits, and the anion gets pumped out. But as it gets pumped out, a chloride can then get pumped in, and then you got channels over here to let chloride into the blood. So, and these are just maintaining the resting membrane potential, also getting pumped into the blood. Distal tubule, this is when water is soluble, but salts are not. Descending, my bad, not distal, descending tubule. So this when water's soluble, it's basically 50% of water is reabsorbed here. And again, it's just going to follow that salt. Aquaporins are open. In the ascending tubule, water, the space between these membranes is closed, so water is not available to go through. It is shut off to water. But salts can now go through. And the main salts that go through here are sodium, potassium, and chloride through this channel, the NKCC2 pump, which pumps all these things. And then we, on this side, going into the blood, with all these different channels or pumps that allow these things to go into the blood. So those are the main three things we're pumping here with no water. In the macula densa cells, the main thing we're doing here is some more chloride. Again, there's more constant. It's like there's always sodium coming in like every step, basically. But chloride is the other thing reabsorbed here. Again, in the distal tubule and the collecting duct, we have these things called principal cells. And the principal cells basically are reabsorbing sodium, and they are reabsorbing sodium and secreting potassium. And a big thing that happens here is that sometimes when we're dehydrated, we need some help from the kidneys to reabsorb more water back into our blood so that we're not letting off a ton of water. So it can change the urine concentrations. Like if we're really dehydrated, it'll suck all the water out and we'll have a very concentrated urine. Or vice versa, if we're really hydrated, it doesn't need to suck as much water out, and so the concentration of the urine will be lower. How that works, which is also covering something else it mentions later on, how that works is we got aquaporins that are stuck on this thing called an ADH receptor. I'm not for sure, but I think it might be a G protein or something. Anyway, aquaporins on here. When we're dehydrated, ADH is released, which is a hormone, comes and binds to this ADH receptor, which then releases these aquaporins. And these aquaporins get stuck on here and then allow for water to come through in this distal tubule / collecting duct. And water follows salts, like we just mentioned earlier. And so we have this another player, aldosterone, which makes more sodium get released, which makes water follow it more. So that's what happens when we're dehydrated. We got some help from these players. Okay, let me see how much I covered. Oh, renal saturation and threshold. Okay, I will do that right now after. Okay, I did that. Okay, renal threshold. Renal threshold is basically where. Let me pull up the chart. Okay, so renal threshold is basically the point at which your proteins that allow reabsorption to happen get saturated, and so you can't really reabsorb it anymore. So a perfect example is with glucose. So glucose, we want every bit of glucose reabsorbed into the blood because we do not want it in the urine. That means we have diabetes and we need glucose for survival. Pretty self-explanatory. So this line is actually supposed to be right along the x-axis. It's not supposed to go up like this. But anyway, the point is, glucose, we're not supposed to have any of it reabsorbed. So we're not supposed to have any of it in the urine. So this should be at 0. We don't want any of it in the urine. However, if those proteins get saturated that account for reabsorption of glucose, they get saturated, and if we have too much glucose, then it'll just stop reabsorbing, and the glucose will start to build up in the urine. And it's like too many people trying to fit through a door at a time. It doesn't let as many people through, and so you get some backlog into the urine. And that's called diabetes. So that is also called renal threshold, is like the peak amount that you're able to hold in those proteins, or that those proteins are able to pump through or reabsorb. So that's what renal threshold is. Now going back down to see what's next. Okay, GFR and clearance. Okay, so GFR is... Okay. Let me find my notes on it. Okay. Well, it's basically just the kind of flow rate of things. So, GFR is saying how much stuff is going through this whole system per some unit of time. Anyway, and so how it relates to clearance. So clearance, I have a little definition over here, is the amount of the amount of something cleared from the plasma per minute. Okay. So, okay, well, I guess for a better definition of GFR, real quick. So, it's the glomerular filtration rate, and it's basically saying how good the kidneys are at filtering blood. So, like, how much fluid is filtered, how much stuff is filtered, how much blood is filtered per minute. And this is what is cleared from the plasma. And it's measured by the concentration of something in the urine times the volume, how much urine we actually have per unit of time, and then over the concentration of something in the plasma. So how this works is that some things get fully reabsorbed, like glucose. Some things get fully excreted. We'll talk about that in a second. And some things are kind of a mix of both, like sodium, for example. We might excrete some and reabsorb some. So clearance, basically how much stuff ends up in your urine, can help us know how well the kidneys are filtering, or aka the GFR. So, but in order to do this, we need something to be fully cleared. Like if clearance is going to tell us GFR, then we need something to be fully cleared. We need like zero reabsorption, because if something is reabsorbed, then it screws up clearance, and clearance will not equal GFR. So to do this, we need something that is small, non-charged, and unbounded proteins, which will go straight through and not get reabsorbed, just go straight through the urine. There's two things, inulin and creatinine. So those equal GFR if everything's functioning correctly. So it's all excreted, and that'll tell us GFR and how well things are working. So yeah, it basically just tells us how well the kidneys are doing its job, GFR, and then clearance helps us determine GFR by measuring things like inulin or creatinine in our urine. Okay, I think I got that. Let me see what's next. Okay, a couple more things. Renin, angiotensin, aldosterone. So, how that works. Sorry, I'm down here. How that works. Okay. So, we mentioned. Well, okay. Let me make sure. Okay. So renin, we talked about this a little bit last unit too, but basically, if we sense a lower GFR, if GFR isn't working how it should be, then we release some renin. And renin, we went through this last unit, so I won't go too deep into it. Basically goes through a couple of different things. Angiotensin gets turned into angiotensin 2, which has multiple different effects. It will constrict the efferent arteriole and the glomerulus, which is going to... Okay, well, the goal is to increase blood pressure, because this means that blood pressure, something's wrong with it. We're not filtering as much, so if something's wrong, we need to increase renin. We need to increase blood pressure and filtration. So it'll constrict efferent, which will increase blood pressure in the glomerulus. It can also vasoconstrict the afferent, which will increase blood, this is just general vasoconstriction. This is increasing blood pressure in general in the body. We also figured out that it could increase thirst, so we drink more water, and that'll increase blood pressure and blood volume. Another thing it can do is increase aldosterone release. And we know, I just mentioned earlier that aldosterone is one thing that helps us move water across. Like so for example, when we saw up here if we're dehydrated, if we're dehydrated, then we need to suck more water through. So aldosterone will release more sodium, which will make water flow more. And if water's flowing more into here, that means we increase blood pressure in here, which is good, which is what we want. So that's how that system works. The goal is to increase blood pressure and blood volume. Okay, now this last part. Okay, so in this last part, basically what happens... Okay, here's a rough drawing. I haven't redone this one yet. It's a little complicated. But basically, on the descending to... Okay, so if we're dehydrated, the loop... Okay, well, let me come up here. I'm sorry. So the loop of Hindley comes down here, right? And so as we move further and further down, we get into this area called the medulla, or the medulla, however you say it. It's like the juxtamedullary glomerulus, the juxtamedullary nephrons. They swoop down into this medulla, and it's really salty down here, which basically is important because if we're dehydrated, when the filtrate passes through here, we need to reabsorb as much water as possible because we're dehydrated. And so we need a really salty concentration down here so that when the filtrate passes through, water follows the salt and it gets released from the filtrate and put back into the blood because we're dehydrated. So this is basically important in dehydration. So how that works is that this is the same for both, except this just goes down lower in the juxtamedullary nephron. But in the descending limb, so we got it coming down here. Descending limb is where, we talked about this earlier, it is permeable to water, but it is not permeable to salts. So water is flowing out. We're losing water. And so as we move down, the osmolarity is increasing. So that's what's making things really salty. So salty equals higher osmolarity. So we're basically just comparing osmolarities. So osmolarity gets higher and higher and higher as we move down. And then on the ascending limb, that's when water is closed off, but it is open to salts. And so if we got a bunch of water in the blood, if we got a high concentration of water outside of here and not much on the inside, then the salts are going to get pumped back into the blood. It's going to get reabsorbed back into the blood. And so we're getting rid of those salts that were making it so high in osmolarity. So if we're getting rid of those, then the osmolarity is going to go down as we move our way up. So you see how that works. The osmolarity gets higher and higher and higher. It gets saltier and saltier and saltier as we move down. And then as we go back up, it gets less and less salty. So anyway, the whole purpose is so we can get water out. And let me see if I'm missing anything on that. So loop of Henle. Yeah, so that osmolarity difference, when it gets really high, gets really salty, that's just a concentration gradient. Okay, explain how this gradient and ADH can work. Okay, so yeah, basically what I mentioned was that when we're dehydrated, we need to suck all the water out, which is going to make a higher concentration of urine. That means our pee is really yellow. It's high concentration. And ADH works with this. We already talked about what happens here with ADH, how it, puts aquaporins there. And so water is able to flow through. So we're able to suck out even more water, making the pee even more concentrated. So that's what ADH does. So it works hand in hand with this part where so that works to concentrate the urine more and suck more water out, and so does that gradient that we talked about. So they work together to suck more water out. So this makes it more salty. ADH puts more aquaporins in there, and then aldosterone makes things more salty, so that water can flow through the aquaporins that ADH put on there, or that the ADH receptor put on there, or that protein put on there. Anyway, so those work together to make the urine more concentrated. And that is about it.